Hi everyone, this is Yuhui Chen, and it's a pleasure to be here today to share our latest work. Vision language action models struggle with zero-shot generalization. In real-world settings, they usually need task-specific fine-tuning to work on new environments or robots. The standard method is supervised fine-tuning, but it has some clear downsides. Firstly, the data often comes from human teleoperation, which is expensive and inconsistent. While we assume human demos are high quality, they actually vary a lot between operators, or even the same person at different times. Secondly, supervised fine-tuning trains the model to imitate what is in the dataset, but this doesn't always lead to task success. The policy may still fail when things go off script or get disturbed. To address this, we look to reinforcement learning as a better alternative. It directly improves the policy using reward signals, which helps it learn more robust and general behaviors. This idea is inspired by how reinforcement learning has been used to align large language models and its strong results in robot control. So how do we apply reinforcement learning for VLA post-training? We propose a two-stage framework built on a consistency policy as the action head. Both stages share the same training objective. In the offline stage, our goal is to get a strong initial policy using just a small number of expert demos. Traditional methods have several drawbacks. Supervised fine-tuning is stable but limited by data inconsistencies. Offline reinforcement learning can improve policy, but it's unstable due to the poor state action coverage and missing negatives. To address these, we store expert data into the demo buffer and train a value function and policy. For the value function, we use calcu-learning, which reduces TD error and as a regularizor to penalize those out-of-distribution data to keep value estimation conservative. For the policy, we use a consistency loss that combines two losses, a behavior cloning loss to mimic expert actions and a value-guided loss to improve performance. Since the value function may be inaccurate with limited data, the behavior cloning loss is important to keep policy stable. In the online stage, we aim to quickly improve the policy. We focus on stable, efficient learning and safe exploration in the real world. To support this, we extend the offline demo buffer with a new replay buffer that stores data collected during training. Since the data comes from the current policy, the distribution shifts gradually, reducing mismatch and making it easier to apply standard Q-learning. For the policy, we keep the same loss from the offline stage. Unlike typical online training, we also keep the behavior cloning loss. It acts as an anchor, keeping the policy close to expert demos and prevent collapse during online fine-tuning. Also, safe exploration is crucial in real-world robot learning since unsafe actions can cause damage or danger. To handle this, we allow human operators to step in any time during training to correct behaviors. The intervention goes into the demo buffer to guide the policy towards safer and more efficient actions, helping the policy converge faster than fully autonomous training. Our method improves policy significantly across 8 real-world robot tasks while keeping safety. On several tasks, we hit 100% success, from simple pick and place to precise pack and hold and flexible object handling. Improving the policy with value guidance achieves better performance than with supervised objective. On simple tasks like picking bread, it not only succeeds but finishes in fewer steps. For harder tasks like hanging a Chinese knot, it even learns to pull down to the knot to check whether it's hooked. Training from scratch with reinforcement learning often takes a long time and needs lots of human help, making it risky and inefficient. In contrast, starting from a pre-trained VLA model cuts down the training time and reduces the cost of online interaction. Our method handles inconsistent data through reward-driven learning, enabling great performance on context-rich tasks, even like threading a needle. It also shows strong robustness to external disturbances. The policy can still complete tasks when the manipulated object is removed or the shape of the flexible object is changed. Thank you all for listening. You can find the full paper and our open source code on the project website. If you'd like to get in touch and discuss further, my contact information is available on my personal website.